Hi, I'm Anna Hoffman, and welcome to this episode of Data Exposed Live. We are super excited to have you all here today. I'm hearing double sound. 1 second. It's like Data Exposed on repeat. Anyways, I'm Anna Hoffman, and welcome to this episode of Data Exposed Live. We're super excited to have you joining us today from wherever you are joining, whether it's Learn TV, Twitch, YouTube, Twitter, wherever you're joining in from today. We'd love to hear from you. So go ahead and put stuff in the chat. We are looking at all of those. We're going to be answering your questions throughout the session. So please go ahead and take a look, ask your questions, make your comments. We want to hear from you. We want to keep this engaging. Now today we're going to be continuing the Azure SQL Security series. There were 2 episodes before this. So if you missed those episodes later, you can go back and catch up on them. Very exciting show today. We're going to be talking about things like transparent data encryption, always encrypted with secure enclaves, and SQL Ledger. So I'm excited to learn a lot. And with all that aside, I want to start bringing up our awesome guests so you can get to know them. The first guest we have today is Shoham. Shoham, thanks so much for joining us today. How's it going?
Hey, Anna, it's great to be here. Hello, everyone joining us today for this session. My name is Shoham Dasgupta. I'm a PM on the Azure SQL team, and I focus on security and encryption-at-rest technologies like TDE.
Awesome. And our next guest we have is, let's see, Jason. Hey, Jason, how's it going?
Hey, Anna, how are you? It's great to be here.
Great to have you. Jason, can you tell us a little bit about what you do?
Yeah, you bet. So I work with Shoham. I work specifically on the Ledger feature of Azure SQL Database. Prior to that, I worked on Azure Blockchain Service. So I've been kind of in the blockchain space for a while and bringing that stuff to SQL. So excited to talk about it.
Awesome, great. And last but definitely not least, we have Jakob. Jakob, thanks for joining us today. Can you tell us a little bit about what you do?
Sure. Hi, Anna. Hi, everybody. I'm Jakub Szymaszek. I'm the same team basically as Jason and Shoham, Azure SQL Security team. I've worked on a number of features over the years, including Always Encrypted and Ledger.
Awesome. So we have a great show today. I'm going to take some of our guests out, but you will be seeing them again, and they're also going to be standing by to answer your questions. Hi, Vishnu. Hi, everyone else joining us from wherever you're joining us. Welcome again. So Shoham, before we get into the show, for those that maybe have joined the series or haven't joined the series, can you take us through a little bit about where we are in this journey of Azure SQL Security?
Absolutely. So we started the Azure SQL Security series a few months back, and we already had episode 1 and 2 so far. So in episode 1 of the Azure SQL Security series, we went over the comprehensive security portfolio that Azure SQL offers to its customers. And this includes the pillars that you see in front of you. These are our fundamental security pillars for each of our security areas. And each pillar contains security features that you would need to implement. And altogether, we walked over how customers can use all of these features together to build a comprehensive security strategy for storing their data in the cloud. After that, in episode 2, we did a deep dive on the first pillar, which is authentication and access management. And this set of features was all about how do you make sure that you're authenticating users correctly into your database, and also assigning them the right access privileges so they can only see the data that they are entitled to. So we did episode 1, which was a walkthrough of all the security pillars. We did episode 2, which was a deep dive into authentication and access management. And now we are in episode 3, where we talk all about the data protection security pillar.
Awesome. Yeah, I'm looking forward to getting right into it.
Sure, let's get right into it. So data protection security pillar deals with all of the security features that protect and make sure that your confidential and sensitive data in the cloud is protected. Now, this has assumed a lot more significance in the recent years because organizations are embracing the cloud more, and they are moving all of their data and assets to the cloud. So obviously, they are worried about the security of their data and is their data being protected in the cloud properly. So data protection contains a list of features through which we make sure that your data is properly protected and encrypted while stored on Azure SQL and on the cloud. Now, encryption is a fundamental aspect of data protection. And at Azure SQL, we make sure that your data is encrypted no matter the state it is in. Now let's talk about the different states that your data can be in. So encryption in transit is basically your data moving on the wire between your client application and your database. And we make sure that any data that is in transit is always encrypted by TLS. Encryption at rest basically refers to your data that is at rest on the disks, and it's in an inactive state and offline state. This could be data in the form of database files, backup files, log files. So we make sure that all of your data at rest is encrypted with a technology called TDE. And thirdly, there is encryption-in-use, which basically refers to data that is actively being used, for instance, for query processing. And we have a feature called Always Encrypted, through which we make sure that encryption-in-use can occur. So let's go into each of these sections in more detail. And let's start with encryption in transit. So like I mentioned in the last slide, all of the data in transit between your client applications and your database server is always encrypted. And we make sure that this is encrypted with transport layer security, or TLS, which is an industry standard protocol for encrypting data in motion. Now, TLS encryption is enforced at all times for all connections. So it's on by default and enforced all of the time. And as a best practice, we do recommend customers, whenever you are specifying the connection strings in your client applications, make sure that you turn the encrypted connection to on and do not trust the server certificate as a best practice. There is also an option to enforce a minimum TLS version on the server. So this is a server property, as you can see in the screenshot on the right-hand side. When you go to the Azure portal, or you can even do it through other means like API and PowerShell, etc. But this is the screenshot basically shows you how you can go into the Azure portal and select the minimum TLS version, which is a property at the server, the database server level. So
awesome.
we all know that TLS 1.2 is currently the most secure version that Azure SQL supports. So for instance, if you were to enforce 1.2 as a minimum version on the server, then any of your clients that are accessing the server from a version lower than that would not be able to access the server anymore. So you can basically prevent any clients that are using insecure versions of SSL TLS from accessing your server in that way by setting a minimum TLS version.
Awesome. So it seems like there are a few pretty basic and standard things you can do for encryption in transit. I just had a quick question. If you set the minimum TLS version, does that apply in and out of the server, or is it one way?
Yeah, that's a great question. So it applies both ways. It applies for all traffic coming into the server and out of the server. And what typically happens is, once you have enforced a minimum TLS version on the server, then the first time a client application tries to connect to the server, the minimum TLS version is verified as part of the initial TLS handshake between the server and the client. So if your client, for example, does not support the minimum TLS version that you have enforced, then the server will deny that request right at the time of the initial handshake, and the user or the application user will receive an error saying that an invalid TLS version is being used. So yes, okay, it's enforced both ways, and if your client doesn't support it, then you will know as soon as you try to connect to the database server.
Okay, cool. That's good to know. Thanks.
Yep. So moving on, let's talk about encryption at rest. So like I was mentioning, data at rest can be offline and inactive data in the form of your database files, your log files, and whatnot. So this is data lying on the disk and not being actively used. And there could be threats against this kind of data. For instance, a malicious user or attacker is able to access the physical disks at the data center. And if it's not encrypted, then they would be able to read that data and get access of your sensitive data. So for this reason, we have the technology called transparent data encryption, or TDE. It's a very popular technology that lots of SQL users already use. And this basically protects against the threat of such malicious offline activity by encrypting the data that is at rest on the disk. The encryption here is real time, and that's where you have the transparent word in the transparent data encryption feature name. So it's real-time encryption and decryption of data, and it's transparent to the application users. So you don't need to apply any changes to the application, but this is enabled by default. So as soon as you create your SQL database, you get transparent data encryption enabled right from the start. Now, encryption and transit that we spoke about before, and encryption at rest, are both table stakes for any cloud service provider these days. And we recognize that encryption at rest is a very important part of compliance and regulatory requirements that organizations are required to achieve. So organizations can basically meet some of their common compliance and regulatory requirements by enforcing encryption at rest and making sure that they don't turn it off once it's being enabled by default. And along with other features that Azure SQL offers, other security features, encryption at rest enables defense in depth protection strategy. So you think of encryption at rest as adding to the security layers that other security layers that Azure SQL already provides. You can never say that encryption at rest is a foolproof or one-shot method to secure your data. But rather, at Azure SQL, we advise that customers should have a multi-tiered security approach. And you can use other features starting from authentication, authorization, network security, and encryption at rest to build a multi-tiered defense in-depth approach as your best security strategy. Now let's talk about the different key management options that are available in TDE. So like I said, TDE is enabled by default. So the first option, which is also the default, is Microsoft Managed Keys. So in this case, Microsoft will own the responsibility of managing your key generation, key rotation, and all of your different key lifecycle management operations. So customers don't need to worry about the keys. Microsoft takes care of all of it. And this is the simplest and easiest option. That's also the default option that customers can use. Now, there are other options for customers who are looking for more control of their key management and need to basically have granular control over the different key operations. So the second option that we provide is called Bring Your Own Key, BYOK, also known as Customer Managed Key, in which case the key management and storage is a shared responsibility between Microsoft and the customer. And by shared responsibility, what I mean is the customer owns all of the key lifecycle management operations, starting from key generation, key rotation, providing access privileges to the key, and revoking access privileges when needed. So the customer owns all of the key operations and the key management, but the key store is owned by Microsoft, and the key store used is Azure Key Vault. So that's why I say it's a shared responsibility between Microsoft and the customer in this case. And we'll talk more about it in the next slide. The third option that we provide is called Hold Your Own Key. So in this one, both the key store as well as the key operations are managed exclusively by the customer. So the customer can basically retain control of their own key, and they can also store the key in a hardware security module, or HSM, that they themselves own and is located in their own data center, for instance. Now, it's important to call out that the Hold Your Own Key, or HYOK feature, is only available in infrastructure as a service, or IaaS, which is basically SQL Server hosted on Azure VM. So if you have a SQL Server hosted on Azure VM, you can effectively store the key in your own HSM and connect it to SQL Server by a technology called Extensible Key Management, or EKM. So we do provide a bunch of key management operations. It really depends on the level of security assurance and how stringent the customer's security requirements are, and they can choose what works best for them. It's important to call out that if you choose the bring your own key or hold your own key option, then you as the customer are responsible for making sure that access to the key is protected, because in turn, the key also protects access to your data. So you basically get more options and more flexibility if you choose the second and the third option, but it also brings more responsibility in making sure you are keeping your keys and your access privileges and whatnot secure. Lastly, let's talk about double encryption at rest, which is something that we have started offering recently. So double encryption at rest refers to two independent layers of encryption to protect your data at rest. And we achieve the two independent layers by firstly using TDE as the first layer, and then providing an optional second layer of infrastructure encryption. Infrastructure encryption is also known as volume encryption or disk encryption, and customers can optionally turn it on to achieve two layers of encryption, also known as double encryption at rest. Now, you would think that why do I need two independent layers of rest, two independent layers of encryption? Is TDE itself not enough? While TDE itself is a very good measure, but typically two layers of encryption at rest help protect against a compromise or a key compromise scenario for a single layer of encryption. And it provides higher security assurance in that way. As an example, you have enabled TDE for your database, and you are using the bring your own key option. But supposing your key was compromised and a malicious user was somehow able to access your key. So in such a scenario, if you have the second optional layer of infrastructure encryption enabled, then the attacker, even though they have the TDE key, they just cannot decrypt your data because it is still being protected by the second layer of encryption. So that's how two independent layers of encryption are better than one. And this is a facility that we provide to customers who are interested and have higher security assurance needs. Okay, let's move on and talk in detail about the TDE with customer managed key scenario using Azure Key Vault. So like I mentioned in the last slide, this option essentially allows you to have more control over your key operations, your key lifecycle management, and in turn ensuring who has access to your data and when. It's also important to call out that the central key management that this enables allows you to do separation of duties in the management of your keys and data. And by separation of duties, what I mean is the responsibilities of your DBA, who's managing your database operations, can be different from, for example, your key vault or your security admin, who's managing your key vault and your keys. So you basically get more control over your key management operations. You are free to generate your key, rotate your key as and when you need it, provide access to your database, or revoke access if there is a breach or when you need to. So you have flexibility in assuming control of all of these things. And like I mentioned, the key store that we use is Azure Key Vault, which is a highly scalable and available cloud-based key store in Azure. Azure Key Vault offers multiple offerings for customers depending upon the level of security assurance that they need. So you can use something as simple as software-backed key vaults, going on to more stringent Federal Information Processing Standard or FIPS 142 validated level 2 and level 3 hardware security modules. So these are specialized HSMs or hardware security modules that protect your vault, and customers have the option of using these more stringent security vaults to store their keys. So you can use any of Azure Key Vault's offerings. We support all of them in Azure SQL. And encryption keys can be generated inside of the key vault if the customer needs to, or if the customer already has a key that they are using, for instance, in an on-premise HSM, then they can simply upload that key into Azure Key Vault and start using it.
Awesome. This has been really useful. I'd love, Shoham, if we could take a look at a demo.
Absolutely. Right before the demo, let me talk a bit more about the separation of duties scenario, and then I'll dive right into the demo. So if you see the diagram on your right, I was talking about how CMK, or customer managed key with Key Vault, enables separation of duties. So you essentially have a DBA here who's connected to your Azure SQL Server and managing all of your data. Then you have a security admin who manages your Azure Key Vault. And how do you now enable CMK for your SQL Server? So the first thing that the DBA needs to do is they need to enable what is called Azure Active Directory identity for the server. So once they enable that, then the SQL Server will basically have what is called a system assigned managed identity, or also known as an Azure Active Directory identity. And this allows the SQL Server to authenticate with the Azure Key Vault. So now that the identity has been enabled on the server, the Key Vault admin or the security admin can go and provision this server's identity the right amount of access on the Azure Key Vault. And the access permissions that we need are get, wrap key, and unwrap key. Once this is done, then the server will be able to read the key from the Key Vault and use it for encrypt and decrypt operations. It's also important that if you have somebody like an auditor who comes in and wants to periodically audit the key operations and the key access on a regular basis, they can use something called Azure Monitor to get a view of all of the recent audit logs and when a particular key might have been used for data access. Now let's move on to our demo. So in here, we'll talk about how do you very easily enable customer managed keys on your server that currently has service managed keys enabled. So let me shift to my Azure portal screen. So in here, you see that I have a server called Contoso Server Episode 3. This is my database server. I am on the transparent data encryption blade. And right when it was created, TDE was enabled by default, and the service managed keys or the customer managed keys option was enabled. So now I essentially need to transition this to customer managed key. So for that, let's move on to my Key Vault. So I have a Key Vault here, Contoso Key Vault demo. And the first thing I need to do is assign my server's identity the right access on the Key Vault. So I've already done that. And what I did is I went to access policies in the Key Vault. I created a new access policy for my server. And the key permissions that I have assigned are get, wrap key, and unwrap key. So these permissions are sufficient in order for the database server to access the key that I have stored in my Key Vault and use it to perform encrypt and decrypt operations on the database encryption key of the data of the database server. Now I don't have permissions to see the key here because just the server has access. But when I had uploaded, I already created a key on this Key Vault, and I have copied the key URL because I need the key URL to configure CMK on my server. So let's go back to my server and configure CMK now. So I select the customer managed key option and I add my key identifier on. This is what I get from Key Vault. I could also choose to select a Key Vault and a key, or I could just choose to directly enter a key identifier. So in this case, I just enter the key identifier, I hit save. And what happens is behind the scenes, SQL service checks that this server has the required amount of the correct permissions on the Key Vault. And then it sends the data encryption key to the Key Vault to be encrypted. The Key Vault encrypts the data encryption key and sends it back to be stored in the database. So we got a success message here, which means that customer managed key was successfully configured. Let's now use a slightly different mechanism to validate that this happened successfully. So let's use PowerShell, but you could as well use REST API or CLI mechanisms to do this. So what I'll do here is I'll first issue a command that gives me all of the encryption keys on this database server. And as you can see on the top, this is the encryption key that I just configured. This is my key vault URI along with my key vault name and the key name that I configured. So I know that this key was added successfully on the server. It also shows me the earlier key, the service or the Microsoft managed key that was there on the server. Now that the key has been added successfully, I also need to verify that the encryption mode has successfully changed to CMK. So for that, let me issue the next command. And in here, I see that the encryption type is set to Azure Key Vault. The server's Key Vault key name is set to the one that I needed, and my Key Vault is correctly configured. So in this demo, what we saw was how easy is it to move your server from a service managed key mode onto a customer managed key mode by having your key stored in Key Vault, providing your server the right permissions on Key Vault. So that concludes my demo, and yeah, hope that demo was useful.
Yeah, no, definitely useful and very cool to see how, there are different ways that we can configure it, whether we're portal people or CLI people, and also how we can manage those different keys ourselves if that's something we want to do. So Shoham, I know we talked about encryption in transit and encryption at rest, but I understand there's one more type of encryption, and for that I'm going to bring up Jakob. Jakob, maybe just to kick us off, can you tell us or remind us again what the difference between encryption at rest, in transit, and in use is?
Sure, absolutely, Anna. So data at rest is data that is stored on disk and database files and backup files, right, as Shoham explained. And the data in transit is the data that is being exchanged on the wire over the network connection between the application and the database system, right? But there is one more state in the data lifecycle which is often ignored and forgotten, and that is when the data is being used for query processing inside the database system, right? So consider this type of an attack where, let's say, a rogue malicious machine administrator, operating system administrator, connects to the machine hosting the database, scans the memory of the SQL Server process, and exfiltrates sensitive information, right? Or even a simpler attack where a DBA connects to the database. A DBA can run an arbitrary query against any table, right? So the DBA can run a select statement and get any data they want. And even if you have TLS or TDE enabled on the database, these technologies will not protect such attacks, right? So that's why we need encryption of data in use, protection mechanism that protects data that is being used in query processing. Now, if you think about it, if security was the only goal and data protection, protecting data in use was the only goal, that would be actually quite easy to achieve that, right? You could just dump encrypted sensitive information into the database, store it in the database, and you would meet your security requirements. But then the functionality of the database system would be dramatically reduced. Basically, right. The database system would be unable to process any queries on this data that is encrypted. So that's not what we want. So what we want, we actually want to achieve two goals that are conflicting and very hard to achieve together. So we want to ensure that the data is protected, these powerful adversaries, high-privileged, unauthorized users cannot access the data. But at the same time, we want to ensure that the database system can reason about the data, can perform computations on the data that is being protected, right? So we call this paradigm, we call this vision, confidential computing, and Azure SQL is unique in a way that it actually does have a technology that addresses these, that achieves these two conflicting goals together, and that technology is always encrypted. So let me spend a couple of minutes explaining quickly what Always Encrypted, its foundational architecture we introduced in 2015-16 is. And so this is the technology that, again, aims at protecting sensitive data in use from high-privileged users, both on-premises and in the cloud, And there are three important things I want you all to know about Always Encrypted. It's important that you understand about Always Encrypted. So element number one, the first fundamental concept is that Always Encrypted is a client-side encryption technology. This is how we achieve the strong security guarantees of protecting data in use on the server side. So basically, the data gets encrypted, decrypted on the client side. The data is never exposed in plain text, and the keys, cryptographic keys used to protect the data, are never exposed in plain text inside the database environment. So admins, DBAs, operating system administrators, cloud administrators even cannot see the sensitive data in the clear or the keys in the database environment, right? The second important thing I want to call out about Always Encrypted is encryption transparency, right? So the key component in this workflow is the client driver that performs dynamic translation between plain text and ciphertext. So what it means is that it automatically and transparently encrypts any data that the application sends to the database, the data that targets encrypted columns. Always Encrypted, by the way, is a column-level encryption scheme. And it also transparently decrypts any data that comes from protected columns, from columns that are encrypted. So the database application, you as a developer, you don't have to worry or know about which columns are encrypted, which are not, and how to encrypt, decrypt data. The client driver handles that for you transparently. And finally, in this initial version of Always Encrypted released a few years ago, we made the first and fairly small, let's be honest, step towards delivering on this confidential computing vision, right? So we basically managed to support one confidential operation, and that's equality comparison. We achieved it through deterministic encryption. And with that, we can support queries like point lookup searches, find me a person with a given social security number, right? Or equality joins, right? So that was this first initial step towards this confidential computing paradigm that we made a few years ago.
Awesome. This seems like pretty groundbreaking technology, at least a few years ago, and pretty advanced at how we figured out how to do the decrypting and encrypting without DBAs having to necessarily know what's happening. But like you said, this only equality comparisons, like maybe that's a bit limiting. Did we keep going?
Exactly. Yes, I agree. It is limiting. In fact, many applications, especially those that aim at or that handle personally identifiable information, names, addresses, phone numbers, you typically need more than equality comparison to manipulate with the data. You need pattern matching, for example, right? And so this initial release of Always Encrypted, this initial architecture, of course, didn't support such queries. And the only option customers had was to move the data from the database to the client side and do these richer computations on the client side, which of course is very expensive and inefficient from the performance point of view, and quite often, to be honest, infeasible if you have a large data set. Similarly, you run into very similar problems when you, let's say, have a large table, lots of data, and you want to encrypt your column for the first time. Again, in order to provide these strong security guarantees, protection of data in use, we cannot allow the database system to perform such cryptographic operations, because that would mean that the SQL Server needs to have access to the keys, and we need to protect the keys from potentially malicious SQL Server environment, right? That's our assumption. That's our threat model. We don't trust the server, which again means that in order to perform such operations, you need to move the data from the server to the trusted machine outside of your database and perform such computations, such operations. They're very inefficient, right? So to address these problems, we spent the last few years researching solutions, and we found a solution which leverages a technology called secure enclaves, right? So from the security point of view, our goal remains the same, right? We want to protect sensitive data from high-privileged users, but we want to expand the functionality. We want to be able to support more queries, more a broader, richer surface area on the data that is protected in this way, right? So for that, as I said, we're leveraging a new technology called secure enclaves. The idea is that, so what is a secure enclave? It's basically a black box, a piece of memory within a process like SQL Server that is basically inaccessible to anybody on the machine hosting that process. Even OS kernel level administrators or DBAs cannot see what's inside the enclave, right? Therefore, naturally, it becomes a great candidate to be a trusted execution environment for processing sensitive information. And that's exactly how we are using it. So during query processing, the query processor inside the database system delegates computations on encrypted columns to the enclave, where the data can be safely decrypted and processed, right? And now we can access plaintext data within that secure environment, so we can support much richer queries. And then in the version of Always Encrypted, which, by the way, is generally available in SQL Server 2019, and is currently in public preview in Azure SQL Database, we managed to support pattern matching, range queries, and sorting, and all of that with indexing and a few more operations, right? So that's one very important benefit of secure enclaves, richer queries, right? But we're also addressing this other problem of encrypting data or performing cryptographic operations like key rotation at scale, right? You couldn't do that until now. Now we can support these operations inside the enclave in a secure way. There is no need to move your data outside of the enclave. And by the way, we just heard from a customer who, until recently needed to run this encryption process in the old way, moving data out of the database, and it took over 20 hours and was still running. And with enclaves, this can be done could be done within 30 minutes or so. So dramatic improvement, right? Of course, the results will vary and depend on your setup schema and many other factors, but it's definitely way more efficient, right? So that's basically what Always Encrypted with enclaves is.
Awesome. This is really cool technology. We did get a question that asked about performance, and I think you kind of hinted towards the answer to that. I'd love if you could just briefly address, how does encryption-in-use impact performance, whether it's with Always Encrypted or with enclaves?
Right, great question. So, well, I would offer kind of two alternative views or perspectives on performance. So one perspective, kind of obvious, is that, well, encryption always adds performance overheads, right? Security is not free. Encryption is not free either. So yeah, if you see this diagram, the data gets encrypted, decrypted on the client side, and is also encrypted, decrypted on the server side. So yeah, there will be some overheads. We did some measurements, and we're gonna share some results in the future, probably some kind of a blog post. But the overheads were not substantial. When we measured it against using popular benchmarks, again, I don't have concrete numbers to share, but yeah, you should be prepared. There will be some overheads. On the other hand, you should always use Always Encrypted selectively to encrypt columns that contain only sensitive information, don't encrypt all your columns in the database. So, if you encrypt just a few columns, overall, the end-to-end impact should be negligible, to be honest. Now, the other perspective I want to offer is that, well, if you think about it, if you have a hard requirement to protect your sensitive data in use, right? What is your alternative to Always Encrypted? The alternative is to encrypt the data, dump it in the database, and then you can do zero computations on that data, right? So in order to do any computations in your end-to-end application, you could have to move the data out to the client side and run these computations. They're very slow, very inefficient. So from that perspective, Always Encrypted with enclaves actually provides performance improvements compared to these alternative approaches. Again, if you have a hard requirement to never expose sensitive data to DBAs, to administrators, including cloud administrators and Microsoft operators, right?
Right. No, I think that's a great, well-rounded answer, and hopefully that helps our Twitch viewer and some of our other viewers that were asking about performance. Now, I didn't mean to interrupt, Jakob. I'd love if you could go deeper and take us through how this enclave attestation thing works.
Yeah, absolutely. Yeah, as we said, enclaves bring these two important benefits: richer computations, in-place encryption, but it also generates some challenges, right? So one problem that enclaves introduce is, if we look at this diagram one more time, is here the enclave, it's supposed to trust as an extension of the client-side boundary. It's like the agent behind enemy lines, if you will, right? It's an entity that represents that trusted client within the untrusted SQL server. So an interesting question is, how does the client actually know? How can it be assured that this enclave is really trustworthy? It hasn't been compromised. It's not some kind of a simulator that is dumping your sensitive data, in the internet or somewhere else, right? So we are solving this problem by introducing the attestation protocol and an attestation service. So the idea is that before the client driver, which is kind of the controller here for this entire workflow, it leverages the enclaves, authorizes the use of the enclave for any computations on sensitive data. It first verifies that this enclave is trustworthy, is genuine. And by the way, we support different enclave technologies in SQL Server using VBS enclaves. In Azure SQL Database, we're using hardware enclaves. So the attestation workflow verifies that the underlying enclave technology is one of these two, essentially, and the code running inside the enclave is what's supposed to be running there, which is the library created by Microsoft for Always Encrypted, signed in a very specific way with a specific signing key, right? So that's what the attestation is about, right?
Awesome. And I think, you're going to talk about it next, but I know that this is only available in a specific hardware today. Is that correct?
Right, exactly. So this is particularly true in Azure SQL Database, where, as I mentioned earlier, very briefly, we're using hardware enclave technology called Inter-Software Guard Extensions, or SGX, which is not broadly available in all our Azure fleet, right? Which means that we needed to give you an ability to basically control where your database is placed, and to give you a way to express that you want to put your database, run your database on hardware that is equipped with Intel SGX. And that's what we did. We added basically a new option in the vCore model under SQL hardware configuration. We call this option DC series. When you enable it, your database is automatically placed on a hardware equipped with Intel SGX, always encrypted with enclaves, is available to you. I want to mention just a couple of limitations that you should be prepared to expect in the near future or midterm future. Number one is that this hardware is available on relatively low performance machines with only 8 cores. That's how many cores can be associated to your database. I want to emphasize that these are physical cores, because hyperthreading is disabled on these machines. So it's not apple-to-apple comparison with, let's say, Gen 5 hardware configuration that most people use. And currently, we only support this hardware in 7 regions. If you don't see your favorite region here on the screen, let us know. We might be able to accommodate your request, right? And one other thing specific to SQL DB that I want to mention is that in Azure SQL Database, as an attestation solution, we are using the new Azure service called Microsoft Azure Attestation. And the nice thing about it, compared to alternative that currently is the only option for SQL Server 2019, is that Microsoft Azure Attestation is a platform as a service solution, right? So it's very easy to configure. It's a policy-driven technology. So you define a policy for attesting your enclaves, which is evaluated before your client application uses the enclave for computations on sensitive data. And that policy, basically, I don't want to go into details now, but you basically state here that you trust very specific code to run inside the enclave, and that code is SQL Always Encrypted library that implements cryptographic operations and rich computations on sensitive data. Yeah.
Gotcha. Cool. This is awesome. Thanks so much, Jakub. What would be awesome is if you have something to show us.
Absolutely. I'm prepared to show a quick demo here. So let's do that. It's going to be a quick demo demonstrating, the value prop of the feature, the main benefits. So here for this demo, I'm going to use a simple human resources HR application that allows me to, manage or view my employee records. I can actually filter my records by employee salary, by a portion of a social security number. I can also sort my employee records by social security number or by salary. It still says processing, so we can give it a few seconds. Yeah, that's what happens when you do the live demo. Your demo gets stalled when you do the slide presentations, but okay, it seems like it recovered, so it still works, and I can filter by all these things and sort by social security number and salary columns. Now, this application talks to a database in Azure SQL DB, and here I'm connected to this database as a database administrator, as a DBA. So I can query, I can do whatever I want in this database. I can run an arbitrary query. However, when I query a table that stores employee records, I cannot see the values in the social security number and salary columns in the clear, because these two columns are protected, are encrypted with Always Encrypted. Right? So I cannot steal that data. I can basically only see ciphertext. I cannot see plain text, so the data is protected. Now, as a DBA, I have also configured an extended event session against this database, which allows me to intercept extended events, which basically capture the queries that generate, right? So here, let's actually look at one of these queries, okay? Let's see how these queries that the app sends to the database look like, okay? So I'm going to reformat this query a little bit so that we can more easily review how it looks like. So as you can see, it's a simple select statement, pulling some columns from the employees table. But what I really want to call out here, which is unique, and you cannot do that with any other data encryption technology, is the fact that this word class contains rich computations on columns, which, as you saw before, were encrypted, right? So the SSN column is encrypted, but we have a pattern matching comparison in this query against the SSN column. We have a range comparison against the salary columns. My columns are encrypted, but the application can still issue rich queries against these encrypted columns, right? Not only that, if we look at parameters, which we need to tweak a little bit here so that we can actually see their values in a better way. So here you can see that even query parameter values corresponding to encrypted columns like social security number, min salary, max salary, which is somewhere else hidden behind the screen, these values are also encrypted, right? The client driver, as we explained before, encrypts these parameters before sending their values to the database. So a malicious DBA cannot even see the query filtering, the filtering criteria that the app sends to the database that is protected as well. So again, the main takeaway from this demo is you can protect your data from powerful adversaries, and at the same time, you can continue running, benefiting from rich query functionality the database system provides.
Yeah, this is a really cool demo, Jakub. I especially like what you were saying. You can allow DBAs to do their job without, letting them see stuff or potentially have malicious intentions and see things that they shouldn't be able to see. Yep. Now, this has been kind of a great encryption story, but are there other tools or technologies in Azure SQL that we can take advantage of when it comes to kind of protecting or hiding sensitive data?
Yeah, absolutely. There is one technology that I definitely want to quickly explain and talk about, and that is dynamic data masking. So this is the technology which is very different from what we've talked about so far, right? So what we talked about so far were encryption technologies, TLS, TD, always encrypted. This is very different. This is not an encryption technology. There is a data obfuscation solution, right? So the idea is that we want to protect data from unauthorized application users. It's very different than always encrypted that protects the data from system admins, right? Here the goal is to protect the data from unauthorized application users. And what we do basically, we mask the data on the fly when the data is being returned from the database to the users who are not supposed to see the data in the clear. We mask this, or this technology dynamically masks or obfuscates the data. We provide a number of masking functions for common data elements or data types like social security numbers, phone numbers, and so on. So you can leverage those existing functions, or you can define your own masking function. And what's important is that the solution is completely transparent to the application, right? So the application will continue to work when you apply this technology. So I want to emphasize there is more of a development solution addressing developers who want to basically easily implement data masking for applications, and this allows you to basically manage in one central place, which is the database, which applications and which users of these applications get to see sensitive information you know, in its original form versus the obfuscated format.
Awesome. Thanks so much, Jakub. This has been great. And I feel like we as a team have a really great story about, you know, protecting data kind of at every stage of where it is or who's trying to access it. So it's been really useful. So thanks so much. Next, what we're going to talk about is something really exciting, really new, and that is blockchain and SQL. So for that, I'm going to bring up Jason, and maybe you can help demystify blockchain and SQL and how these things go together.
Absolutely. Thanks, Anna. So far, what Jakub and Shoham have been talking about has been encryption of data. There's another element that's important when we think about protecting data, and that is protecting it from tampering. Now, blockchain has been, you know, all the rage the past few years, and enterprises have been flocking to blockchain primarily because it provides an immutable record of data that can't be tampered with and changed, which is really helpful if you have a multi-party business process where some of the parties in that business process don't trust one another. Think of a supply chain as an example. And so having that immutability that comes with blockchain is really attractive. Now, one of the challenges that we've found is that many customers that want this level of digital trust, if you will, don't have the need for the decentralization of a blockchain. And when I say decentralization, what I'm talking about is a blockchain requires that every party that participates in it hosts infrastructure. That infrastructure has to be connected, it has to be governed the same, and it's very challenging from an infrastructure and from a business process standpoint to set up. But systems that are fundamentally centralized, so think of systems that are in databases today, don't need to be decentralized to provide that level of tamper evidence. And that's exactly what we're doing with Azure SQL Database Ledger, is making data tamper evident through cryptography. And it's very similar cryptographic elements that we use in blockchain today that we'll walk through. Now, in addition to that, we provide a historical record of all of the changes that have actually happened in the database. So one of the benefits of Azure SQL Database Ledger is, unlike a blockchain, you can do updates and deletes to your database, but still track it and detect that tampering if there's tampering that's occurred in that data. And importantly, being able to then provide cryptographic proof to other parties that may be consuming that data. That could be other business parties, or it could be auditors. That data has not been tampered with is really powerful. Beauty here is that it's really just the SQL that you already know and love today. That means that you don't have to change your applications. There's no new T-SQL API to learn. It's really just a function of SQL that we've added that provides this level of digital trust without all the complexity that a traditional blockchain may afford. So let's talk a little bit about what's actually happening here and what we're doing. So we've implemented or introduced the concept of ledger tables inside of Azure SQL Database. Now, ledger tables are not a new table type. They're a property of existing tables. So you effectively can turn it on for your existing tables very easily. But we'll first talk about the two types of ledger tables that we have. And the first one are called updatable ledger tables. So as I mentioned before, being able to do updates and deletes. So how do we do that? So let's assume for a second that I'm doing an update to an updatable ledger table, changing a row. What actually happens when the transaction comes into the system, that the row that's been updated is actually, that historical value is moved into a history table, and the new value is in the updatable ledger table. Now, those of you that are familiar with SQL are saying, it sounds a lot like temporal, Jason, and it is. It's really extending temporal functionality to a degree. And that extension really comes in where we're adding additional metadata to the tables themselves to be able to track the lineage of those data changes. So for example, when that transaction comes in, we associate a unique transaction ID to it and the order of operations of which rows were changed in that transaction. So that way you can actually go back after the fact and be able to see what's happened, what transaction made what changes in the system. Now, to make it easy to view, we've actually created a ledger view. What that does effectively is pulls together the updatable ledger table and the history table so you can actually get a chronicle. Here's the current value of this row, here's the previous value of that row, and so on. Now that's all data lineage information and just historical tracking. Let's talk about the cryptographic elements that are involved here. So what I'm showing is a logical diagram of what we call the database ledger, which is effectively a blockchain data structure. So the data itself is cryptographically protected through the database ledger using cryptography, SHA-256 specifically, as well as what's called a Merkle tree. So let's talk about what a Merkle tree is. Otherwise known as a hash tree. Effectively what happens is every row in a particular transaction that comes into the system is hashed using SHA-256. So hashing is a little bit of can be a complex topic, but effectively what happens is you have an input. In this case, it's the number of columns in the row, the first column ordinal, and so on. Runs it through the SHA-256 algorithm, which then produces a hash, which is basically a 32-byte string of information that is completely obfuscates what that data is. Now, every row, once it's hashed, we hash those rows together. So as you can see here, the hash of row 1 and 2 are hashed together to create hash 1, 2, and 3, 4, and so on. This is the Merkle tree aspect of it, creating what's called then a parent hash for those two rows. This continues up until you get to the very top, where you have effectively a root hash that represents all of the data elements in that Merkle tree. So in this particular case, for the transaction, all the rows that were hashed in that transaction are then represented by a single root hash. Now, we call this root hash, or what we do with this root hash is we then use it for transaction hashing. So let's go to the next step here and then talk about what happens there. So each transaction itself, using that previous root hash for the transaction, again, we go through the same process for all of the transactions that are happening within a given period of time. And so that given period of time is what we call a block. So during a 30-second interval, all of the transactions that have occurred during that time are then hashed together, up again, creating a root hash for that particular time period of 30 seconds. We call that particular root hash that represents those transactions in that time the database digest. So the database digest itself represents the state of the database at that time that that particular block was created inside of the database itself.
Okay, and so these blocks at the bottom, I'm just going to stop you to make sure I'm following correctly. These blocks at the bottom, this is kind of the blockchain, right? Because the block 0 is linked to block 1. Is this really like the same technology that blockchain is using?
You're exactly right, Anna. This is effectively what Ethereum, for example, does today in other blockchains. By creating each block, the hash of that particular block is actually cryptographically hashed using the block of the previous hash. So it chains them together, which means you have to hack all of the blocks in order to be able to hack the database, which is theoretically impossible to do.
Okay, cool, thanks.
Now, this database digest, or that root hash for that block, once we've created that, we push it externally outside of Azure SQL Database into a trusted storage location. And the reason why it needs to go into a trusted storage location, or I should say a tamper-proof storage location, is that those hashes are the root of the database trust at that particular point in time, and what you use to then verify the data later, which I'll talk about. But let's talk about that trusted storage for a minute. So trusted storage in this case, we've built into Azure SQL Database Ledger to be able to connect directly to Azure Storage Immutable Blobs. That ensures that those digests can't be tampered with, but also a new service called Azure Confidential Ledger, which is a tamper-proof storage service. So Jacob talked briefly about Always Encrypted with secure enclaves in SQL. Using that same enclave technology, Azure Confidential Ledger protects those digests in a very deep way, effectively removing anybody from the trust boundary, even Microsoft, from being able to get into those digests and forging those digests.
Cool.
And that's important because if I want to then verify that my data has not been tampered, or an external party like an auditor wants to verify that my data has not been tampered with, what you then do is you issue a stored procedure that references the digests that are stored in trusted storage. We then recalculate all of the hashes in the database real time to make sure, or to determine if they match or don't match what was in the trusted storage. If they don't match, then we know a tampering event has occurred. So what do I do at that point? Well, at that point, what I would do is use the forensics information, the transaction tracking ID, the service principal, et cetera, to understand where the changes made in the database. And then I can restore my database to an earlier point in time and be able to correct the data in the main database itself. So that's updatable ledger tables. Let's talk about another table type, or another table property of ledger tables called append-only ledger tables. It's effectively the same at the cryptographic level, which you'll see up at the top. The primary difference here is that we are blocking the ability to issue updates or deletes at the API layer. So think of issuing a T-SQL statement to update a row. That actually will fail inside of SQL. Now, this is important because this provides an extra level of security. Specifically, a DBA or privileged user would not be able to then tamper with the data by just issuing updates and deletes inside of the database. So that's the table structure itself inside of Azure SQL Database Ledger. Let's talk a little bit about how do we actually enable and use this functionality. So there's a couple of ways to enable or use ledger tables in Ledger. The first is when you create a new SQL database, you'll notice in the create experience in the portal, there's a new tab called security. And you'll find things there such as Azure Defender for SQL and other properties. But what you see here is there's a new area called Ledger. Now, this is not configured by default because there are some things that a user needs to do to configure this that require some implicit decisions. So if you click on this Configure Ledger button here, you'll see a new pane that gives you the opportunity to create a ledger database effectively. So what is a ledger database? A ledger database means that all of the tables inside of this database when I create it will be automatically created as updatable ledger tables. So you don't have to worry about whether a table is not protected or not. Now, this is optional. You don't need to do this here. I'll show you in a couple of minutes how you can do this specifically through T-SQL, but this is the easy button to ledgerize your database, if you will.
Ledgerize, I like that.
The next setting you'll see is the digest storage. So I talked about the trusted storage. So as I mentioned, supporting both Azure Storage and Azure Confidential Ledger. And again, it's important to protect those digests. So in the case of Azure Storage, you'd want to configure an immutability policy to ensure that those digests are protected. But we build this automatically. Now, if you want, you could not use the automatic digest storage. You could pull those digests yourself by running a stored procedure and save them yourself. But this is just, again, a way to make it a bit easier and to orchestrate the system together. Now, once I have created my database, I can go back in and to manage the experience. There's a couple of things you'll notice here. In the security tab, there's a new ledger function here. You'll see effectively the same user experience, but one thing you'll notice is that this ledger database checkbox cannot be unchecked. Now, this is by design. This is a security consideration to ensure that the Azure tenant administrator couldn't go in, uncheck that checkbox, make changes to the database, and then check it, and nobody would be the wiser. So this is a one-way option to ensure that it's protected. Also to note, I talked about Azure Storage. Azure Confidential Ledger is currently in preview. It's free right now, so great time to try it, but at some point when it gets to GA, it will be charged. Now, note that Azure SQL Database Ledger, however, since it's a feature of Azure SQL Database, there are no additional charges. It's just a core security fundamental that we've enabled.
Jason, one quick question I have on that previous slide. You talked about enabling at the database level, but then I can also create ledger tables. If I don't have it enabled at the database level, can I still create ledger tables? Is there some sort of guidance there, or I'm just confused?
No, that's fine. We try to give a lot of options, which can be confusing in some cases. But yeah, so let's say that to your point, I want to create a database where I want to have a mix of ledger tables and non-ledger tables. And yes, you can absolutely do that. So you could uncheck that during create and not do that. You could still then configure the storage for digests. And then what you would do is when you create a table, you would specify this argument here, ledger equals on. In this case, this will create this table as an updatable ledger table. If I added the append only argument to it as well, that would then make it an append only ledger table. Okay. So in this example, what I'm going to show is I'm just going to create a very simple schema of a bank account balance. And I'm obviously turning ledger on here. One thing to note, I should have mentioned as well, is that a database can have a mix of updatable ledger tables, append-only ledger tables, or no ledger tables at all. It just depends on how you want to configure it yourself. So let's go forward. We've created this particular table schema here. So let's say that I'm going to now, with this new table, I'm going to add a new customer to this bank account, and with an opening balance of $50. What you'll see here is that each transaction has that transaction ID I mentioned before. In this case, Nick Jones with a $50 deposit has a transaction ID of 1104. Okay. Now let's say that I want to issue a transaction that has it's going to add multiple parties to, or multiple customers to this bank. So John, Joe, and Mary with varying balances. So you'll notice that not only is the transaction ID the same for that because it's a single transaction, but if you look over at the ledger start sequence number, you can see the actual order of operations that transaction happened. So you know which happened first, second, third, etc. So this gives you, again, that ability to do the data lineage and forensics tracking of changes that have happened in the database. Now let's do an update. Since this is an updatable ledger table, we're going to update Nick's balance to $100. So what you'll see here is it's now $100. There's a new transaction ID, 1202, because that's a new transaction that issued that. Now the previous row, or the previous value of that row, has been copied over to the history table. As you can see there, ledger transaction ID 1104. Now, the way you would actually view this, again, would be through that ledger view I talked about. And as you can see, Nick's update is showed as a delete of the previous row, which was moved into the history table, and then an insert of that $100. So you get, again, that chronicle view of the ledger over time by using the ledger view. So let's talk about the blockchain level under the hood. The way the blockchain is implemented is effectively in two new system tables. The first is called database ledger transactions. This lists here, as you can see, all of the transactions that have occurred inside of the database itself, as well as the commit time of those transactions, also capturing the principal name of the user that made those transactions so you know who did it. And then, of course, the hashes that I explained earlier in the Merkle trees that represent those particular transactions. The next table is database ledger blocks. So this effectively lists all of the blocks that have been created in the database. And then since this is the first table I created in this database, there's only one block with a block ID of 0. That root hash, or that database digest, if you will, of that block, the size of the block, which is 4, so there were 4 transactions, and the previous block hash is null because this is the first block. So if there's another block that showed up, you would see that it would have the hash of the previous block there, forming that blockchain.
Got it.
So now that we've talked about setting up and tracking the data, let's talk about that process of verification. How do I verify the database? So if you go back into the portal, there's 2 ways to do it here. One, you can do it in the portal. As you can see, the manage experience, there's this verify database command in the toolbar. If I click that, that will generate a T-SQL script that you would use to then run the verification. So let's dive in and see what that would look like. I could run that in Query Editor here, or I can go over to like Azure Data Studio or SQL Server Management Studio. So this script, effectively, what it's doing is it's querying the locations where I've been storing my digest. So over time, I could have used Azure Confidential Ledger and then switched over to Azure Storage. We coordinate all of that so you don't have to worry about moving your digests. So we're going to query those locations, and then we're going to run the verified database ledger from digest storage location stored procedure, which references those digests and again recalculates those hashes and gives you the results. So there's two things here in the results that are interesting. The first is the digest locations. So in this case, what it's going to show is where those digests were, and I'll show you that in a second. The second obviously would show the result. Was the verification successful, or was there a tampering event?
Mm-hmm.
In that digest locations, you can see here that I've had 4 configured over time, a bunch of different digest locations. But what's important to show here is which one's the currently configured one, which is current true. In this case, it's my Azure Confidential Ledger, and all the previous ones that show false were the ones that were previously configured. Now, this is important because an advanced attacker could actually point to a different storage location with forged digests. So inspecting this when you run your verification ensures that it's pulling the digest from the locations that you actually configured.
Gotcha. This is pretty cool. It's also cool you can see a history of what's been used, and we just track that for you.
Exactly. So the core scenarios where we see Ledger as being really helpful is, number one, just streamlining the audit process. And so when I say the audit process, that could be an internal audit, such as for a line of business application for your internal organization. It could be external audits where you have external auditors come in. Being able to provide an auditor cryptographic proof that your data has not been tampered with is really powerful. So we see it as just a core security fundamental technology where if you have any production data that you want to protect from tampering, Ledger can do that for you. Now, we've also seen it as an alternative to blockchain-based solutions. So again, where Ledger is really powerful is where you have, again, a centralized solution where other parties that may participate in your business process trust that central party, but they want to verify. So they have the ability to then verify that. So we've seen many customers who were going down the path of a blockchain where they really didn't need it, turning to SQL Ledger as an alternative. Now, in addition, Azure SQL Database Ledger is a great addition to an existing blockchain. And the reason being, blockchain systems are notoriously difficult to query. They're not designed as an OLTP type system for that purpose. So a typical pattern that has existed would be for customers to take their blockchain and take that blockchain data and stream it what they call off-chain to a database. But as soon as you do that, you lose the immutability guarantees of the blockchain. Well, with Azure SQL Database Ledger, you can now maintain that integrity from the blockchain to the off-chain data store in Azure SQL Database. So to give an example of the auditing process, I'm going to go ahead and turn it back over to Jacob, who's going to walk you through a really cool demo that extends upon the demo he showed earlier. So Jacob, take it away.
Sure. Thank you, Jason. Okay. So let's actually resume where we stopped the previous demo, right? So I'm logged still as a DBA to the Contasa HR database, and I can query the employee tables. Actually, the DBA I'm impersonating happens to be also an employee of the Contasa company. His name is Jay Adams, right? And we're looking at his employee record right here. So as we explained before, when we talked about Always Encrypted, Jay, who is a rogue DBA in this scenario, he cannot steal or exfiltrate sensitive information stored in SSN and salary columns because these columns are encrypted. They are protected with Always Encrypted. But so we kind of covered on this attack vector. However, Jay can try to tamper with the data, right? So Always Encrypted makes the tampering scenario slightly more challenging for Jay because he can also, let's say Jay wants to maliciously make an unauthorized raise update of his salary, give himself a raise essentially. So how can he do that? So since the salary column is encrypted, he cannot just insert an arbitrary value there because he doesn't have access to the keys that would allow him to encrypt that value and insert the proper ciphertext in the salary column since the column is encrypted. But he can try something else. So let's assume that Jay knows that Catherine, another employee at Contasa, Catherine holds a high-level position, so Jay makes an assumption that Catherine likely makes more money than he does, so she has a higher salary. So an attack that Jay is going to try is basically to replace his salary with Catherine's salary. So by executing this simple update statement, right? So now, sometime later when this HR application refreshes, it picks up a new Jay's updated salary, which happens to be the same as Catherine's salary. Now this application shows that in the clear and plain text because it can decrypt it, as we explained before. So Jay is happy and he's hoping for a nice paycheck in the next paying period. However, unfortunately for Jay, this employee tables was created as a ledger table, which means that all the updates, all the changes, any user triggers against the table, all these changes are preserved, captured in a cryptographically protected ledger-backed data structure. So again, unfortunately for Jay, a few weeks later, another user comes in and logs on to that system, to that application. That user is Alice, and she plays a role of an auditor. So to begin her routine review of changes in the Contoso HR database, Alice starts with verifying the ledger, running the ledger verification to actually ensure that she can trust the data she's going to review subsequently. So in the next step, Alice clicks on this employee ledger tab, which basically pulls the data from the ledger view for the employees table. And that view, as Jason explained, is a chronicle, is a journal that captures the history of changes against employee records. And here, Alice can easily find the records indicating that, first of all, Jay's salary was updated, increased, and she can also see that it was Jay who has made this change, right? And because the ledger data in the ledger data structures has been cryptographically verified, we know the data is genuine and it hasn't been tampered with. It will be impossible in practice for Jay to deny that he was the one who made this malicious change, right? Now, let's look at another example of an attack scenario. In this example, a malicious bad actor is not a DBA, but it's another employee at Contoso who is an HR team member. So her name is Rachel, and Rachel uses this HR application. And Rachel decides to, let's say she's a close friend with Francis, and she wants to give Francis an unauthorized salary raise. So for that, she uses this HR application and goes here and changes the salary to a much higher number, saves the results. So now the same story with the auditor. A few weeks later, auditor comes, and as usually, the auditor should and would start with verifying the ledger integrity, and then she would review the data in the ledger view for the employees table. And now, as before, the auditor would notice the suspicious and very high percentage-wise increase of salary of one of the employees. But now the challenge is that if we look here at the username column, this column doesn't provide a lot of useful information this time, right? So basically, it states that these changes were performed by the web application. This is the identity that we see in this column. This is the identity, the managed identity of the Contoso HR application that is, by the way, deployed running in Azure Web Apps, right? So we cannot tell who actually was the application user who triggered those changes. We only know that the changes were triggered through the application. Unfortunately for that attacker, Rachel, this application has been instrumented so that any query, any update SQL query that users of these applications trigger against the database through their actions using the UI of this app are persisted, are written to another table, which its name is audit events. And it's also a ledger table. In fact, it's an append-only ledger table. And it captures the query statement, the name of the user, and the time the query was issued and executed, triggered by the application user. So back to the auditor story right here. When the auditor next clicks on this audit events tab that pulls the data from the audit events table, the auditor will find the query statement that clearly updates the salary of one of the employees, and the name of the user, the application end user who triggered that change, right? So what I showed you in these two attack scenarios, in these two attack examples, is that a ledger basically helps ensure non-repudiation because the data is cryptographically verified as genuine. These attackers cannot be effective in denying they have made the change, right? So as Jason said, Ledger in this case helps streamline the auditing process and makes this process fast and easy.
Wow, this is so powerful and very, very interesting. And it's cool how simple it is and how it's all using T-SQL. I just have a few questions after watching the demo, and then we have a few questions on Learn TV. I think we have a few extra minutes. So for the second piece with Rachel, we're using an append-only ledger table. But Rachel isn't blocked from doing the update. We can just now audit that an update was made. How does that work?
Right, so not exactly. So there are two tables here. Let's clarify that, right? So there is an employees table. This is the main table that is a backend of that, OLTP system, this HR OLTP application, which can issue insert, update, delete statements against the employee tables, and all these changes are preserved, right, and cryptographically protected. Yes, so Rachel, the malicious user, can issue an update statement against the employee table to update somebody's salary. There is nothing stopping Rachel from doing that. But all the changes, these changes will be preserved. However, because there is this web application in the middle, we know that the application has done these changes, but we don't know which user. Now we also have another table, and that table is an append-only table, that audit events table, right? So what we capture here is basically the result of instrumenting this web application, which, whenever you click on the edit button and then make a change, let's say in the web app, you trigger the update statement. And what the application does, it inserts that update statement, it adds a new record to the audit events table. So we do not expect any other operations against this table other than inserts, which is why it has been intentionally created as append-only table. And you cannot, so basically whatever any statements and queries you persist there cannot be even modified because there is no API for it, right? Insert and update and delete statements are blocked, only inserts are allowed.
Wow, that's really cool. It's cool. So we're using a combination of technologies and strategies to make sure we can track everything, but ledger tables make it really easy for us to do that, basically.
Yep, that's the object.
Awesome. And then one question that came through is, this capability is pretty new. Which regions is SQL Ledger supported in today?
Right. Today, SQL Ledger is in the process of being deployed to Azure worldwide. Currently, as of today, I believe, and Jason can correct me here, I think it's supported in a couple of regions. Jason, can you chime in and remind me and tell all of us which regions we are supporting Ledger in today as of now?
Yes, as of today, and I just checked, we are in West Central US, but we're rapidly rolling out, so we expect to be in Brazil South, West Europe, North Europe very soon, so just keep your eyes peeled for that. We'll have updates in the documentation that show what region it's in, but if you want to try it today, West Central US is the place to give it a shot.
Awesome. Okay, that's great to know. Thanks, Jason, for hopping in there. Also, I just wanted to share with everyone watching and our presenters specifically, we've gotten a lot of really positive comments through Learn TV, Twitch, Twitter. One comment we got is really amazing to see this new tech. I was so excited to see it roll out. Someone also said, this Ledger feature is my favorite from Microsoft Build. So lots of excitement about Ledger, as well as the Always Encrypted and other capabilities you all have shown to us today. So Jakob, as we look towards wrapping this segment, can you just kind of take us through a summary of what we've done, and also for people following the security series, what's going to be next?
Sure, absolutely. So in a previous episode, we discussed authentication and access management, and today we covered our data protection pillar. We talked about encryption technologies, TLS, TD, Always Encrypted. We talked about dynamic data masking for obfuscating data and making data inaccessible to unauthorized application users. And we talked about Ledger, the newest and really exciting technology that we just roll out at Build. So that's what we discussed today, and we will continue our journey through all these different security pillars. We have 3 more to cover, so that's our plan for the next few months.
Awesome. And let me just, for folks following this series, what I wanted to share is that there are lots of resources for you to learn more. So if you check the description for this video, you will be able to dive into all of the topics you saw today, which I recommend. There are a bunch of really interesting documentation and even a new white paper on SQL Ledger, so definitely want to check that out. Additionally, if you're following this series or forgot that this is part of a series, this is the 3rd episode, like Jakob mentioned, in this Azure SQL Security series that we're doing. If you missed the other two episodes, or you want to watch them again or revisit them, they are time-coded and located at that aka.ms URL at the top. You can also find them on our YouTube channel if you subscribe to our YouTube channel at Azure SQL YouTube. And just a sneak peek, Jakob mentioned these as well, but this is our tentative calendar for when we're thinking about airing the next episodes in the series. So you'll want to check back in August for the next episode on Azure SQL Security. Now I'm just going to bring up the rest of our speakers today, just as we close out. I just want to thank you all so much for joining us. I learned a lot. I know this was a long, jam-packed episode. I think our viewers have learned a lot. It's very clear in the comments and some of the feedback we've been getting. So thank you so much to our speakers, and to our viewers. Thanks so much for joining us. I know, sometimes security is a heavy topic, but you can tell there's a lot that we're doing. And I think, each of the speakers mentioned how, security is really a big priority when it comes to protecting your data, and in this case, data protection. So thanks to our viewers. If you like this video, go ahead and give it a like, subscribe to our YouTube channel. We stream live on Learn TV every Wednesdays at 9 a.m. And we hope to see you next time on Data Exposed.